Today we are going to discuss about the fundamentals of probability distributions and um, the concept of random variables, probability density functions, etc. And we start with some preliminary definitions of probability distributions. So, this is the fundamental first concept. The concept of random experiment may be familiar to most of you. And formal definition is an experiment with more than one possible outcome. The outcome cannot be predicted with certainty before the experiment is conducted. And the set of all possible outcomes is a well-defined set called the sample space. And the sample space usually denoted by either omega or capital S. So here, by the term well-defined, what we mean is that if a particular element is given, then we can say that we can identify whether that particular element belongs to the sample space or not. So that's the meaning of the term well-defined. Now, let us have some examples. First one is coin tossing experiment. We have a coin, and the coin has two different faces. One is we call it as head, and the other one is called as the tail. Now, if we toss the coin, then we have two different possibilities: either a head turns up or a tail turns up. And if we collect the two possibilities together in a set, then it is a non-empty set, and this one is an example of a sample space which is associated with the experiment of tossing a coin. Now, the second one is again tossing or throwing or rolling dice, and if we roll a die with six faces, which are marked 1, 2, 3, 4, 5, and 6, then the possible outcomes are 1 turns up, 2 turns up, 3 turns up, 4 turns up, 5 turns up, and 6 turns up. These are the possible outcomes. So we can call it as the sample space associated with the experiment, random experiment of rolling a die. So obviously these experiments satisfies the conditions. It has more than one possible outcomes, and the set of all possible outcomes is a well-defined set, and we cannot predict whether one turns up, two turns up, or three turns up. So this is all examples for random experiments. Now, the third one is counting the alpha particles emitted by a radioactive substance over a fixed period of time. So here, if we count the number of alpha particles emitted from a radioactive substance, so we keep a certain amount of radioactive active substance, and we can observe the substance for a time period, say t, maybe 5 seconds or 5 minutes or 5 hours, so we can just 5 seconds, and we count the number of radioactive particles emitted from this particular substance. We count it using some counting uh, mission, something like Vega counter or like that. Now, if we count the number of alpha particles emitted, it can give outcomes like 1, 0, 2, 4, 5, 6, etc. These are the possible outcomes. It can vary from 0 to 0, 1, 2, 3 up to infinity. So it can be 0, 1, 2 up to infinity. These are the possible outcomes. And this is again a sample space. And anyway, when we discuss about radioactivity, we have the term like half-life period of a radioactive material. But that's the concept which related to the total substance. If we have 1 kilogram of a radioactive substance, then after the half-life period, the remaining quantity of the radioactive material become 1 by 2 kilograms. So that's the concept of half-life period. But if you consider a simple atom, an atom of a radioactive substance in uh, collection, then that particular atom may or may not decay during a particular time period. So that is a completely randomized process. So this is again an example for a random experiment. Then if you observe a particular computer and if we uh, measure the lifetime of a computer, then it's again a random experiment for an electronic equipment that can say that can uh, work for a certain period of time that may fail after a certain period of time, and therefore the computer may keep working maybe after 25 years, 30 years, 50 or 40 years, or even after 100 years. That is possible theoretically, and it can damage maybe just at the time of first starting itself. So it can vary from 0 to infinity. And since we are measuring the time, it can vary from 0 to infinity continuously. That's possible. Anyway, when we use a measuring instrument, we can only measure the time as a discrete parameter. But in theory, it can vary from 0 to infinity as a continuum. So that's the sample space associated with the lifetime of a computer. So these are a few examples in which we illustrate the concept of sample space. Now, uh, in the first case, the sample space contains only two elements. In the second one contains six elements, one, two, three, four, five, six, etc. So they contains only finite number of elements. In the third case, we have infinitely many elements, but there is a property. It is a countable uh, set. So finite sets are also countable. So this is countable, but infinity. The S3 is an infinite set. And the last case, it is not a countable set, not a finite set. It is an infinite set, and it is an uncountable infinite set. So these are examples of sample spaces. Now, the sample space can be either finite or infinite. It can be either countable or uncountable. Now, by the term an event, there is a next definition. The term event is referred to a subset of the sample space. Strictly speaking, an event is a subset of a sample space for which we can associate a probability. So, if you consider the coin tossing experiment with the sample space HT, then the set H, a head tensor, is an event. The set T, a tail tensor, is another event, and a head or a tail tensor is a third event, and there is another possible event, neither a head nor a tail tensor, that is contains no elements, that is the null set. That is also an event. So here, if you collect the possible subsets of S, then that will give um, the collection of events. So these are the four events possible for um, for the random experiment of tossing a coin. So we can associate probabilities to these events. So obviously the probability to have neither a head nor a tail is obviously equal to 0. So there is um, the concept of events. Now, obviously, the union and intersection of events is again an event, And there's another term which is to be remembered, mutually exclusive events. Two events are said to be mutually exclusive. Say if A is an event and B is another event, then A and B are mutually exclusive if A intersection B is the null set. So in this particular case, head is an event, tail is an event, and the intersection of head and tail is null set. So head and tail are mutually exclusive events. But if you consider another example, consider the coin tossing experiment with the sample space 1, 2, 3, 4, 5, 6. They are the possible outcomes. Then we define an event as as an even number turns up. Even number turns up. So the set is nothing but 2, 4, and 6. And we define another event E3 as multiple of 3 turns up. So the event is set 3, 6. Then E1 and E2 are not mutually exclusive because their intersection contains a single element 6. So this is not a mutually exclusive events. So this is a concept of mutually exclusive events. And we can also define another concept, mutually exhaustive events, which means A and B are said to be mutually exhaustive if A union B is the sample space. So in this case, if you consider even as the even number tensor and E3, E4 as some say E4 as an odd number tensor, then even union E4 gives the total set. So that's the concept of mutually exclusive events. Now we can define probabilities or we can assign probabilities to events. Now, how we can find the probability of an event? So if we have, so before discussing how to find the probability, we have in our hand the concept of sample space, the sample space one knowledge set associated with a random experiment and an event, say, let E be an event. And we are looking for a probability that an event E occurs. So how we can find this particular probability? So there are three different approaches to calculate the probability of E. Uh, the first method is known as the classical method in which we collect the sample space. We have the sample space, and if you have the sample space which contains a finite number of elements, and if E is a finite set, or obviously if S contains a finite number of elements, obviously then E also contains a finite number of elements. Then the probability of E is given by number of elements in E divided by number of elements in S. So if we have S as associated with the coin tossing experiment, head and tail, and E is the set head, then the probability of E is given by number of elements in H or number of favorable outcomes as we usually 10. Uh, the number of favorable outcomes is 1 and the total number of outcomes is head and tail, so 2. So that's our required probability. So that's the classical approach to probability. We distribute the total probability of 1 to all possible outcomes. And in a similar way, if we toss a die or if we roll a die, then there are 6 possible outcomes. And if our event is an even number turns up, then if you look at the probability of E, then favorable outcomes is there are 3 even numbers, so it is 3 divided by total number of outcomes is 6, so it is equal to 1 by 8. 3 by 6 is equal to 1 by 8. So that is how we calculate probabilities in our classical approach. So here we make an assumption that all the possible outcomes are equally likely, or the probabilities of each and every outcome are the same. But in practical cases, this need not be true. So if we have a coin, then probability of head and probability of tail are equal as per our classical approach. But the coin may not be a fair coin. There may be it may be a biased coin in which probability of head and probability of tail may differ. There may be a higher chance to get a head. That's possible. So we cannot assume that the coin is a fair one. So that's a problem associated with the concept of classical definition of probability. Then there is the frequency definition of probability, which is a experimental method to find the probability. And the process is simply a statistical method. If we have a coin, we toss the coin, say, n number of times, and we count the number of times at which the head turns up, let it be f. Then we count the ratio between f and n. Then, as the number of tosses or number of repetition of the experiment become infinity, the ratio between f and n, if this ratio tends to some quantity, then this number p is known as the probability of our event. So in this coin tossing experiment, if you have a coin, say coin with a coin which is tossed say 10 times, so we tabulate it. We toss the coin 10 times and we get 5, exactly 5 heads. So our unit is head answer. Then f by n is 1 by 2. Then we toss the coin 100 times and the number of head stands up is equal to say 51, and in that case the ratio f by n is 0.51. Then again we toss the coin some thousand times and count number of heads stands up. Let it be 509. So the ratio is 5.09. So it is something near to zero point 0.5, and as the number increases, if the ratio between f and n converges to a number like zero point 0.5, then we say that probability to have a head is equal to zero point 0.5 and the coin is a fair coin. But if what we get is something different, say if the number of heads turns up is something like here if the number of heads is equal to 2, and when we toss 100 times number of heads stands up is equal to 26, and when we toss it 1000 times the number of heads that turns up is equal to 258, and so on, then obviously here the ratio between f and n is not zero point 0.5 or near to zero point 0.5. So here what we get here is here is 2.2 and here 0.26 and here is 0.258. So if we consistently get a ratio like this, then obviously we can say that the coin is not a fair coin, and here the probability to have a head is something near to zero point 0.2 or zero point 0.3 or something like that. So as we increase the number of tosses, this may converge to a particular number, but it is not a number which is near to zero point 0.5. So it can may approach to 0.25. So it's a coin for which probability of head is equal to 0.25, and naturally probability of tail is equal to 1 minus 0.25, because only there is only two possibilities, and it is 0.75. So this is a method by which we can calculate probabilities in a practical way. But the problem here is simply tossing a coin 1,000 times or 10,000 times or 1 lakh times is a time-consuming process, which is not a simple task. Just theoretically saying is very much straightforward, but actually doing the experiment is not a simple one. And okay, if you toss a coin, this is not a big issue. You can stimulate, or we can write a program or something like that, and simulate this particular experiment using a computer. That's all possible. But if our experiment is something related to, say, shipment of related to an experiment, something like, uh, say medical field, testing of a particular medicine in a number of persons, then this kind of definition is not going to work, because we cannot test the medicine for a large number of n and count the number of favorable outcomes. That's not possible. So there's a problem associated with the uh, concept of frequency definition of uh, probability. But it's a practical way to find the probability of a particular type of outcome. Now, there is the axiomatic definition of probability, which is a method which we are going to use in our discussions, and it is compared with the modern definition of probability, and it followed many methods in modern mathematics, and is consistent with the modern mathematics. There's a um, use of, that's the advantage of the modern definition of probability. Anyway, the modern definition of probability, or axiomatic definition of probability, here we defined the probability as a set function defined from, say, if we collect the set of all subsets of S, it is a sigma field, and if we can define a probability set function from the sigma field to the real number system, which has uh, some properties. First one, probability of any event is always greater than or equal to 0. And second one, probability of the sample space is equal to 1. And the third one, probability of A union B is equal to probability of A plus probability of B, provided A intersection B is equal to the null set. If we can, or if we are able to define such a set function from the sigma field, or in simple words, you don't have to use the sigma field or something like that. I think it's enough to use the power set of S. So in our discussions, that's enough. So if you consider the set of all subsets of S for which we are looking for the probabilities, so that is power set of S. And from the power set of S, if we define a set function, by the term set function, we mean a function in which the input is a set. Here the input is a set and output is a real number, which satisfies the conditions like probability of P of E is greater than or equal to 0, P of S is equal to 1, and P of A union B is equal to P of A plus P of B. If all these conditions, if all these three conditions are satisfied, then it is known as the set function P is known as a probability. So that's the axiomatic definition of probability, and this is the definition which we are going to use in our discussions. And we are not going deep into the theoretical discussion of the concept of probability and say the measure theoretical approach of discussion of probability and such and like that. We just define the probability and we just move on to the concept of probability and random variables, etc. directly, and it's not a deep theoretical discussion of probability. Okay, anyway, if we consider this definition, then we can define, we can consider some examples. Say, if we toss a coin, the sample space is head and tail, and if we consider the set of all possible events, it is the singleton set head, singleton set tail, and the empty set, and the sample space itself, that is H and T. So this is our S, this is the null set, and these are the two possible events. Now, if we assign probabilities, if we define a set function which assign a probability to each and every events, then say like 1 by 2, probability of tail is equal to 1 by 2, then probability of sample space is equal to 1, then obviously the probability of null set is equal to 0. So this is an assignment which assigns probabilities to each and every events, and which satisfies all the three axioms of probability, and this is a probability. And instead of assigning P of h is equal to 1 by 2, we can assign P of h is equal to 1 by 4, P of tail is equal to 3 by 4, and P of s is equal to 1, P of s phi is equal to 0. This is again another probability which can be defined over the same random experiment, same kind of random experiment. So any such assignment, if we assign probability of head is equal to P, probability of tail is equal to 1 minus P, head is equal, probability of S is equal to 1, and probability of phi is equal to 0, that's another probability which can be assigned here. So in a similar way, we can define different probabilities associated with different random experiments, and so that's the meaning of our definition. Now, let's just our concept of random experiment. Simply speaking, random experiment is a function defined from the sample space to the real number system. We can think about a random variable for which the outcome is a complex number. That's possible, but we are just restricting our definition to real valued random variables anyway. And here, x is a random variable in which the input is an element of our sample space, and output is a real number. So when we observe at the random experiments which we discussed earlier, most of the random experiments has a real number as the outcome. So in practical cases, say if we measure the height, weight, etc. of a person, or income of a person, or life of a particular electronics equipment, or the marks of a randomly chosen person, or marks obtained in a particular subject. All these things are actually real numbers. So, in our most of physical experiments, what we are looking for is a real number. And without loss of generality, we can assume that the output of a random experiment is a real number. But in some cases, say in the tossing a coin, you can have two outcomes, head and tail. They are not real numbers. So to overcome such situation, we can define a function from the sample space to the real number system. So if the output itself is a real number, then the random variable it can be a say can be the identity mark itself. So we can assign say 1 to the head and 0 to the tail. So the sample space can be replaced with the set 0 1. 0 stands for tail and 1 stands for head. And we can say that probability that the random variable x takes the value 0, probability that the random variable x takes the value 1, and so on. All these kind of expressions are possible, and this is a mathematical expression. Instead of writing probability that a head stands up, we can write probability that x is equal to 1. So it's some clear mathematical expression, and this will help us to analyze the situation in a mathematical way. So that is how we use the concept of this random variable. Now, it's a function different from the sample space to the real number system. And there can be two types of random variables. One is continuous type and the second one is discrete type. In continuous type random variables, the random variable assumes a continuum of values. And as in the case of sample space, a sample space can be a finite one, a countable one, and a continuous. So in a similar way, a random variable also can be a continuous one and a discrete one. Discrete one in this particular case, tossing a head or tail or observing the number that ends up when we roll a die. The random variable takes only a finite or a discrete number of values, and if we count the alpha particles emitted from radioactive substance, then there also we can have only a countable number of outcomes, and that lead to the concept of discrete type random variables. And if that is not the case, if you observe the say life expectancy of say an LED light, then it can vary from say 0 to infinity, and it is a continuous type random variable. If you measure the height of a person or weight of a person, then it can also vary from a certain number A to B, say from 100 centimeters to 200 centimeters. So in that case also, it's a continuous type random variable. Then there is a practical problem. Even if it is a continuous random variable, while measuring it, we measure almost every quantities in as a discrete uh, quantity. So, in practical sense, most of the random variables are discrete in nature, but if it contains in sufficient number of possible outcomes, can be considered as a continuous type random variable. Okay, anyhow, we can move into the details while we discuss problems. Now, here onwards, we are concentrating on discrete type random variables for the time being. And for a discrete random variable, the discussion of continuous random variable may be included in our next session. So in this session, we are concentrating on discrete type random variable, which that is a random variable x takes only a finite number, either a finite number of elements or a countably infinite number of elements. If x takes only a finite number or countably infinite number of elements, then it is a discrete random variable. And for a discrete random variable, we can define the probability distribution as f of x is equal to probability that capital X is equal to small x, si or xi. So if we have a numerical sample space, then we can write like this. Otherwise, we can write f of x is equal to probability that the random variable x takes a particular value xi. So if we consider the coin tossing experiment, the sample space is head and tail, and now we can define uh, a function from S to R, and in such a way that head is equal to 1 and tail is equal to 0. So that's our random variable. Now we can define f of 1 is equal to probability that x is equal to 1, and the random variable x takes the value 1 when we have a head turns up, and if the coin is a fair one, then the probability is equal to 1 by 2, and f of 0 is equal to probability that x is equal to 0, and if the coin is a fair one, then this probability is equal to 1 by 2. So that is how the probability distribution, the concept of probability distribution works. So let's consider another example. If we have a coin, say, or if we have okay, if you have a fair die, and if you toss the die and count the number that turns up, then the sample space is 1, 2, 3, 4, 5, and 6. And since it is a fair die, all the probabilities are equally distributed, and probability of 1 is equal to 1 by 6, probability of 2 is equal to 1 by 6, and so on. And here our random variable is um, defined from the sample space to the real number system, but as the output in this experiment, what we measure in this experiment is already a real number, so we don't have to define a new function. The identity map will work in our case, and it's nothing but the identity map. So x is our identity map, and x takes the values 1, 2, 3, 4, 5, and 6. And we can think about probability that x is equal to 1, probability that x is equal to 2, probability that x is equal to 3, and so on. And probability that x is equal to 6. These are the possible values of xi. Then since the coin is a fair coin, all the probabilities are equally distributed, and the probabilities are 1 by 6. So that is how we calculate probabilities for using the concept of random variables. Now, in each case, how we end up with the concept of random variables. So that's the part of the definition of experiment. What we are actually going to measure is our random variable. That's a simple way to identify the random variable. Now, there's another concept, cumulative distribution function or distribution function, usually abbreviated as CDF or DF, cumulative distribution function or distribution function. The probability density function is usually denoted as PDF or probability mass function. And usually probability mass function is represented by the uh, small f of x, and the cumulative distribution function is represented by capital F of x. So that's a conventional method which we are going to use in our discussions. Now, the probability cumulative distribution function is defined as probability that capital X less than or is equal to small x. So in our experiment of throwing a die, then we can think about probability that x is less than or is equal to say 3. So actually it is probability that x is equal to 1, 2, and 3. and this is equal to 1 by 6 plus 1 by 6 plus 1 by 6, that is 3 by 6. So this is what we mean here. If we sum up the probabilities and 2x, that will give the cumulative distribution function. So, and by the way, if you are looking for in a random variable, if x is a random variable, if you are looking for a less than or equal to x less than or equal to b, if you are looking for this particular probability, then in a discrete case, what we do is we find out the values of the random variable x, which lies in between a and b, and find the value of f at xi for each value of xi, which takes a value into a and b, and we sum up. We clearly write like this: in my summation, f of xi for all xi's which are between a and b. This is how we calculate probability of a less than or equal to x less than or equal to b. And using the concept of this probability cumulative distribution function or CDF, we can find the probability that a less than or equal to x less than or equal to b as f of b, capital F of b, minus f of a. So that's another application of CDF. For many random variables, there are uh, tables which tabulate the values of CDF for different values of A and B, and that can be used to calculate probabilities. Now, there's another definition which is very much useful um, in the discussion of probability, and that is expectation. As the name indicates, expectation of a random variable is the expected value of that random variable in a long run, and that's defined as in a discrete random variable, expectation of x is equal to summation for all values of x into f of x, that is x into probability of x. Let's consider a simple example. If we toss a coin, then the possible outcomes are 0 and 1. And 0 has a probability 1 by 2, 1 has a probability 1 by 2. Then the expectation of x is defined as 0 into 1 by 2 plus 1 into 1 by 2. And this is equal to 1 into 1 by 2, that is 1 by 2. So, if a coin is tossed and 1 stands for a head answer and 0 stands for a tail answer, and at no point of time we are going to get 1 by 2 as the output. Either the output is either 0 or 1. But if the coin is a fair coin, then in the long run what we are going to get is the average of what we get is always equal to 1 by 2, or that is almost equal to 1 by 2. Or if we count the throwing a die problem, then expectation of x is equal to the possible values of x are 0, 1, 2, 3, 5, not 0, it is 1, 2, 3, 4, 5 and 6. So the expected value is 1 into 1 by 6 plus 2 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6. That's equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6. That's equal to 1 plus 2, 3, 6, 10, 15, 21 by 6. So that's equal to 7 by 2 is equal to 3.5. And in this case also, we are not going to get 3.5 as the outcome of this particular experiment. For if we throw a die, we are not going to get 3.5 as an output. But if we list down, or if we tabulate the number that we get as an outcome of rolling of a die, a fair die. And if we repeat the experiment a large number of times, say 1,000 times or 10,000 times, then if you calculate the average number of that tabulated values, then what we are going to get, or what we get is 3.5. So that's the concept of expectation of x, the expected value of x. Now, this expectation has some significance, or a lot significance in our discussion of random variables and probability. And we just give two very fundamental and very useful uh, use of expectation of x. First one is the mean of a random variable, and mean is defined as expectation of x, or in other words, expectation of x for a random variable is termed as the mean of a random variable, and the expectation of x minus mu. Mu is used to represent the term mean, and this is mu, and mu is used to represent the mean of a random variable, and expectation of x minus mu the whole square, or expectation of x square minus mu square, will give the variance of a random variable x. Then, as in the previous case, mean is a measure of central tendency, or at which value the random variable, or the average value of the random variable x is the um, meaning of or mean. Then, as we know, the striking rate of a batsman, or the average height of a person in a class or in a population, the average income of a person in a particular district, all these are the all these are actually mean, and that's the sense of the concept mean. Then the variance. Variance is a measure of how much the values are scattered. So if say if our mean is something here, mu is here, and the random variable can occur or take values from say minus a, or say a to b. These are the possible values of a and b. Then A has a particular probability, B has a particular probability, the mean has a probability, and all the elements in between A and B has certain probabilities. Now, in a population, if you have a population, uh, then a characteristic follow a probability density function, or a characteristic of the population follows a probability density function uh, with the mean mu. Then the average value of that characteristics is mu, and the variance will give a measure of how the characteristics is scattered throughout the population. So, for example, if you are dealing with the income distribution, with say the average income being some 500, and if you have a small variation, then almost all the elements in the population is uh, going to have an income which is very near to 500. And if we draw a curve of the income distribution, it is something like this. Most of the people have a population which is very near to 500, and only a few number of persons going to get an income which is very less than 500 and very greater than 500. But if we have a large variance, that means that we are going to get a curve like this. if we plot the income in that community, then the number of persons with income 500 and number of persons with income very less than 500 and very greater than 500, larger than 500 have almost the same probability or more like the same probability. So that's the concept of variance, and sigma square can be used as a measure of variance. So in our discussions, when we come across a particular type of random variable, say if we discuss about a random variable x, our first step is to find out the probability density function, and second step is to find out its mean and variance. In some cases, we will also find the capital F of x. Anyhow, the next two important steps are to calculate the mean and variance of the random variable. And now, that's the concept of mean and variance of random variable. And here we are going to discuss about two types of discrete random variables. One is binomial random variable and second one is Poisson random variable. Okay, we need a lot of time to discuss about these two random variables. I'm just giving here the probability density functions of these two random variables, and we will discuss about these random variables in a new session. So if x is a random variable, and if x has a probability density function f of x as ncx p raised x 1 minus p raised n minus x, and x can take values 0, 1, 2, 3 up to n. Then this, if we have a random variable with this particular probability density function, then this random variable is known as a binomial random variable. And the probability density function, this here, is known as a binomial distribution. And in our next sessions, we are going to discuss about the mean and variance of binomial distribution, or in which cases or in which situations we can use binomial distribution, etc. Here, I just give the probability density function of binomial distribution. And in a similar way, if we have a random variable for which the probability density function is e raised to minus lambda, lambda raised to x by x factorial, where this lambda takes a non-zero positive value and x is equal to 1, 2, 3, 4, 5, 6 up to infinity. So it is again a countable discrete but countably infinite values. So the sample space takes infinitely many values. If the probability density function has this particular form, then it is known as a Poisson distribution, and the random variable is known as a Poisson random variable. And again, we will have a particular separate section for Poisson random variable, in which we discuss about the situations in which Poisson distribution arises and the problems which can be addressed using Poisson distribution. Anyway, before concluding, let us list down something related to probability density function described here. Here, if we have a probability density function f of x, then we can simply list down a few properties of probability density functions. One is probability density function p of f of x is a probability, and hence it is always a positive number. So a probability density function takes a positive value, And second one, if you sum up all the probabilities, say if we sum up all the probabilities, this is equal to 1. So these are the two important properties of PDF. So there's two identifiable properties of probability density function, and if you have a function in the reverse way, if you have a function which have if that function has these two properties. So arbitrarily, if you have a function f of x, we have a function f of x which is always positive, and if we sum up the values of f of x for all possible values of x, uh, then the sum is equal to 1. If those two properties are satisfied by a function f of x, then that function can be treated as a probability density function. So to define a probability density function, or to have a probability density function, it is not necessary to have a random experiment or a random variable. We just find out a function f of x which satisfies two conditions, then it will work as a probability distribution. But not all that kind of functions have practical importance, and a few of them have practical significance. Few of them have very much very useful functions which can be used to solve a number of real life problems, and that kind of functions are studied separately, and these two functions, the binomial distribution and Poisson distribution, and two of them which has practical significances. And anyway, what we have to what we kept for further discussion are, first one, the analysis of binomial distribution and the situations in which binomial and the analysis of binomial and Poisson distribution, and the situations in which these two distributions may arise, and we will have some problems, and we also derive the mean and variance of these two distributions in our next sessions. And so far we discussed only about discrete type of random variables, and we can have another type of random variables which is continuous type, and we will discuss about continuous type random variables in our following session. And the definition of probability density function for a continuous random variable is something different, so that will also addressed in our next session. So for the time being, thank you. We'll meet again with a few discussions on probability density functions and random variables. Thank you.